guest today is Brian Gaucher, and I've been looking forward to this one. Brian and I crossed paths during his time at IBM, where he spent over 2 decades, and what a 2 decades. He started a wireless department from scratch in the early 1990s, became the IEEE voting member who helped shape the 802.11 standard. That's the standard underneath Wi-Fi, the thing most of us can't live without, and then kept reinventing himself, running P&L on chip design teams across 4 countries, building the Watson Jeopardy betting algorithm, and eventually leading quantum systems engineering, designing the cryogenic control electronics that make superconducting qubits actually work. Brian recently co-chaired the NSF's ERVA report on engineering quantum technologies, and its central argument really stopped me in my tracks. They claim the bottleneck holding quantum back isn't really physics anymore, it's engineering. We have most of the science. What we don't have is reproducible, scalable fabrication, the industrial base to go from cool lab experiments to deployable systems. Brian puts it simply, we need to go from lab to fab. What I especially enjoyed in our conversation was how Brian's experience building Wi-Fi standards kept surfacing as a lens for quantum's future. He draws the parallel directly. The explosion of innovation that followed 802.11 standardization is exactly what quantum needs, but we're stuck in a chicken and egg problem where you can't standardize before demonstrating quantum advantage, yet you'll be overdue the moment you do. We also got into the semiconductor cautionary tale. The U.S. led in research, but let manufacturing go offshore. And Brian argues that quantum is at the exact same inflection point now. I was also surprised by how much of the report is about quantum biology, biosensing, implantable quantum devices, things I had no idea, frankly, were this far along. So if you've been wondering what it actually takes to turn quantum from a science project into an industry, this conversation lays it out. This episode is brought to you by Qubits OK, a dedicated job board and research digest for quantum computing. If you're building a career in quantum or hiring for one, this is the signal in the noise. They also run a daily archive digest that surfaces the papers that actually matter to your specific research interests. Well over 100 archive authors already subscribe. Subscribing is free. Head to qubitsok.com and sign up in 30 seconds. And if you're hiring in quantum, use the code NEWQuantumEra-50 for 50% off your first job posting. The link is in the show notes. And now, my conversation with Brian Gaucher. Thanks for joining me, Brian. I'm really interested in hearing more about this report that you led the writing of. But first, I'm really interested in your own journey. You're 21 years at IBM, working initially on millimeter wave antenna, I believe, and then sort of transitioned into quantum engineering. What was that? What led you on that journey?
Well, it's kind of interesting. My background, of course, is an electrical engineer and hardware designer by training. I spent like 10 years in a government facility doing military R&D before coming to IBM. And then I joined IBM, and they didn't have a wireless department, and I started one many years ago, back in 1993 or 94 timeframe. And we did Wi-Fi, Bluetooth, ultra-wideband, cellular, all kinds of things you wouldn't expect an IBM to be doing. And we actually owned a cell phone company at one point.
I didn't know that.
Yeah. So it was kind of fun. And we had a design center in San Diego and then eventually one in Chelmsford, Massachusetts. And it was all really around semiconductors, right? What can we do to drive volume in certain technologies? And that was one way of doing it. And the wireless was really a lot of fun. And I was the voting member in the IEEE for the standards. We'll talk a little bit about standards for quantum too, because I think it's in the future an important element. But wireless for Bluetooth didn't exist. ultra wideband, and Wi-Fi. So I helped to develop the standards and led the development of Wi-Fi enablement and Bluetooth enablement on ThinkPads. And we designed our own chips actually for doing that as well as the antennas. And that went really well for a while. And then my vice president came to me and said, you're doing interesting things, but you should get some experience outside of research. And I'd been in research, I don't know, 10 or 12 years at least by then. And he sent me up to a division to do a profit and loss management of 100 folks on our chip design. And so I did that. And I led a team of like 50 or 60 in India, 50 or 60 in the US, and then some in China and Japan and others. So that was a lot of fun, really hardcore when you think about profit and loss and what it all takes. So I did that for a while, and I got invited back to research to start up some AI initiatives and what we were doing. And so we called Smarter Energy was one of the things we delved into. Really, how do you use AI to do better oil and gas exploration or manage renewables into a grid? And totally different theme than anything you'd expect on wireless or something like that from the background. So we did that, and my team actually developed the betting algorithm on Jeopardy. So that was fun too. If you ever heard Jeopardy, betting, $32.62, that was one of the outcomes of that, which was kind of fun.
Interesting. So I guess
And
that sort of speaks to the advanced, sophisticated mathematical modeling that underpins any machine learning model that is what we popularly call artificial intelligence at this point, right?
exactly, yes, exactly. And bringing this stuff to life was always fun for me. And my vice president was getting involved in quantum and asked if I wanted to participate in that. And I'm like, wow, that's a really far afield from what I normally do day to day.
Yeah.
But I started to look at things in a totally different perspective. Yes, I was a hardware systems engineer, and I was used to doing things at the chip level and making systems from there. But here you're starting to look at a system at the higher level, right? And it includes everything from hardware and software and how the system and applications all work well together. So I started to get involved in quantum, and it isn't so much from the physics background, but from the engineering. And I think maturity lagged in a lot of the things we were doing there as well. So how I brought stuff to life, getting a standard made was part of that step. And that was important to getting volume production, because if everyone's building on something separate, then you can't leverage what everyone else is doing.
Hmm. And
Quantum is
what was that standard, if you don't mind me asking?
IEEE 2.11.
Okay.
And
Oh, on the wireless side. I thought you meant on the quantum side. So you mean the wireless standard you were a part of?
yeah. So
Got it.
quantum doesn't have a standard,
Right.
but
was
I
gonna
think it
say.
needs a standard, right?
Yeah.
And everyone's going to fight over it. You remember the VHS, Betamax,
Yep. And the
all
Unix
of it.
wars.
Yeah, exactly. Unix wars. So, something's going to happen. And I think somebody needs to take leadership and drive that to make this stuff scalable and reliable and manufacturable. But for me, quantum was exactly the inflection point where you needed to start thinking about a lot of the system and architectural level things. Yeah, you can do stuff at the lab phase, right? You can do, we'll call it cool science experiments, physics experiments. But now the challenge is in integration, reproducibility, and eventually deployment. And NSF came out and was thinking about writing a report in quantum and how to translate deep technical advances into engineering frameworks that policymakers, industry, academia, researchers can realistically build upon. And until we have some common basis, it's going to be everybody from themselves, and it's going to be low volume, and it's not really going to take off. Something's going to have to give. And at least this report is one way of trying to address that. And also, part of the reason the report exists is looking at US leadership in quantum science. It's always been strong. But I think engineering is now the limiting factor. but the global competition is just going up through the roof. They're making huge investments, right? From China to Europe to Japan. So, this is a call to arms in a way, right? How do we drive more investment in a coordinated way? So, I think the core message of the report in the simplest terms is scaling versus discovery, integration versus, isolated performance, systems versus components, right? Quantum advantage isn't gonna come just from better qubits alone, but really from better engineering. The physics is truly exciting and the discovery aspects, but that in itself is not gonna go anywhere without a bigger picture wrapped around it.
Right. Right.
Like, the whole thing is like going from lab to fab,
Right, right.
with a
Well, and
system.
it's interesting you're saying engineering is the bottleneck. In the recent, interview in Design News, you were saying that, you don't think that this quantum technologies are gonna require a new, sort of profession, but rather, adapted skills and capabilities from the existing disciplines of engineering. Is that it's that reskilling or adjusting the skill set, or is it just raw numbers of people with the skill sets that's the bottleneck?
Yeah, I think that's that's true. It's gonna be important to get a transdisciplinary collaboration going, call it engineering, physics, computer science, and specific domain expertise. No one person is going to be able to swallow everything, but I think now there's a bigger, broader set of skills you need to have to be successful in quantum. And, so workforce development, I think that's a big part of it.
Your path from RF to quantum engineering is an instance of that, moving into it, or moving into quantum from, traditional engineering disciplines. Are there things from that experience that you sort of draw on to inform your perspective on what you think is required?
Well, yeah, in a way, I think to be successful, you need to be adaptive. Things change much faster than they used to. You could spend your entire career in a single discipline and be happy and do really well. Today, I think a couple of things are happening. There's so much change going on and so much motion. If you can't move with it, you'll get lost. And so that speaks to a broader exposure to some of these other disciplines and the ability to move fluidly across some of it. In my own case, I started as a double E and then got into what I'll call systems engineering. How do you look at this from the top down, and the bottom up together? I think that's where you start to see the perspective of what's needed. Any good engineer is going to come up with a concept, but it doesn't go anywhere until you can break it into piece parts that a group of people with a specific set of skills can go off and build, and then you bring it back together as a whole. And those people who can see that picture, I think, will succeed more so than just the people who are doing a single bit of it. And I had to learn a lot in each of the areas. I managed in AI, it was a whole software team of folks. And that was new to me. Yes, I wrote software like crazy myself, but it was a necessary thing. And I didn't do a good job, in terms of what some of the professionals would be doing. But it gave me exposure to a whole new host of things and way of doing it. And I think from a building quantum, we really had to do a lot of things like that. So I'm seeing more people coming in with more exposure to these kinds of things. And I think from a schooling education perspective, you'll see the curricula change, right, to help get those folks prepared.
Right. Yeah. So you mentioned, sort of, cool science experiment and, requiring sort of the application of engineering discipline to turn that into something that's, reproducible at scale and deployable. Um, in the report, it cited that sort of superconducting qubit fabrication was sort of seen as just an engineering problem, as early as like 2016, but we still see today, non-standard approaches to fabrication. There, I wouldn't call it sort of a standardized sort of semiconductor, like industrial process yet making qubits. It still seems very scientific, like a science experiment. What do you think is holding that progress back?
So, mm, kind of a long-winded answer, but let me walk through this and just wave your hand if I'm talking too much.
Yeah, sure.
Um, in the report, you'll see that we broke things out into materials, biology, computing, and AI. There were a host of other topics, but these seem to capture a good sense of what's going on and what's needed. And I'm going to put materials up first, and this speaks a little bit to what you were just asking about. So when you think about materials, from discovery to scalable integration, the limiting factor is increasingly engineering precision, not the lack of theoretical understanding, right? So, across computing, sensing, and bio applications, you have surfaces and interfaces that dominate noise, loss, and decoherence. Defects and vacancies limit yield and stability, and biological environments introduce additional variability. So, the engineering bottleneck, we understand the fundamental physics. What we need to do is get to reproducible scalable fabrication, and interface control remains one of the limiting things. So for quantum computing, sure, low loss superconducting and semiconducting interfaces are important. Stable qubit material stacks, cryogenic compatible packaging and interconnects. I mean, even just from a cryogenics perspective, we have these standard fridges and maybe you fit 1,000 or more of qubits. That's not going to be a system in the end. We need hundreds of thousands to millions. So we have to interconnect many fridges as well, right? So, there's a lot of bigger systems problems to work through. And then we have surface chemistries engineered for stable and biological environments. Another thread on top of what we need to build at the device level, and materials optimized for low noise operation outside controlled labs, right? It needs to happen everywhere and be easy. So nano manufacturing at the atomic layer precision. We need industrial scale tools and compatibility. Then there's an integrated metrology, high sensitivity defect detection, inline monitoring and feedback. Essentially, transformational progress requires not only discovering new devices, but kind of engineering reproducible, integration ready platforms across computing, as well as sensing and biological applications, right? That's part of what the report talks about too. So I think the materials touched on what you had originally asked about and how we go about addressing some of the problems there. And if I missed your point, let me know.
No, I mean you're definitely touching right on. I mean, to me, what seems central in the report is this challenge of. I mean, you've already put it in words that how do you take cool science experiments and turn it into an industry? And in a way, what you're talking about is setting the clock back on the semiconductor industry to now nanoscale engineering as the industrial engine instead of sort of this leveraging quantum mechanics for doping and making semiconductors in a integrated microprocessor. It's almost starting again from scratch and building the entire industrial base at that nanoscale engineering level. And it feels like what you're saying is the pieces are all in place, and what needs to happen is pulling that together into that industrial engine. Is that fair to say?
Yeah. Yeah. So let me put it a slightly different way. So we call it the semiconductor ecosystem, right? Um, we can draw a lot of lessons from what we did right and what we did wrong when we started that whole endeavor. Uh, we know scientific leadership alone doesn't guarantee you long-term manufacturing leadership. I think the US, remains strong in semiconductor research and design, but manufacturing ecosystems went offshore and other people took over those things, right? We got globally distributed over time. So a key lesson in that translation infrastructure, fabrication facilities, supply chains, even the workforce and standards, they have to evolve alongside that discovery. The exciting physics has got to go along, but you don't wait until that's done to go and build these things, right? It's a bit of trial and error. So once manufacturing ecosystems become geographically concentrated, you can't rebuild this stuff. It is what it is at that point, and then you have to work around it. So you need to, kind of address this stuff earlier on in the um, whole system.
Right, right. I mean, in a sense, like the for example, like the CHIPS Act was an attempt to onshore manufacturing of the semiconductor industry. But as you said, it's very hard to put the horse back in the barn after
Yeah,
it's
yeah, yeah,
left.
exactly.
And this is an opportunity to start from scratch, as you said, like nanoscale engineering as the theme, the cohering theme across all these different disciplines to build computing devices, communication devices, sensing, and biological. I mean, that was the part actually that surprised me the most. Was were you intending for biology, quantum biology, to play such a big role in this report, or was that surprising to you?
You know, I co-chaired this, and there were Psycat Gua is the other co-chair, and his expertise is also in more in that area. So, and there were some wonderful folks, Jennifer and Fruz, and some others who led the work in biology. And so, your the answer to your question is no. I had no idea that was going to be such a prominent. It was very surprising and kind of exciting to me to
Very.
see that happen. Right, all these biosensing medical devices. Uh, in vitro, when you put something inside somebody, what are the effects? And I didn't know we were doing all of that kind of work, to be honest with you, right? I was siloed in kind of AI and quantum and that sort of area. So I learned a ton and I was really surprised. But, I do think, the net sum of all of this is we're going to need to be able to do investment, but not in isolation, but coordinated development across academia, industry, national labs, and capital markets to make sure these scientific advances translate into something that's durable, a real technological capability. And it's going to take work and it's going to be iterative, right? And I hope we can have the stick to itiveness to do it right.
Yeah. Yeah. I mean, we had the National Quantum Initiative, I think, signed into law in 2020. It's due to be reauthorized. It's overdue to be reauthorized. Are there other things that the federal government should be doing in your mind to try to help this nascent industry sort of coalesce?
Um, Trying to think. I mean, this moment is a weird one. We're no longer really asking whether we can do this. We've demonstrated it, but we have to show this across sort of multiple platforms. So, how do we get the right folks involved? Government funding. I think the focus has largely been on proof of concept stuff. The bottlenecks are, we've shown here to be engineering driven from, materials and defect control and precision. So a lot of work and investment that could be used there. And shifting from discovery to that integration is the pivotal. Decisions made now are going to affect the infrastructure and workforce and coordination to shape all these quantum technologies. So global investment is one of those areas, and I think our government needs to do a lot more comparably to what China and Europe and others are already doing. So, I think there's that big investment side of things that's needed.
Yeah, and I mean, I feel like in a sense, I mean, certainly Illinois is an example of state level investment. And in some ways, the Chicago Quantum Exchange was formed before the National Quantum Initiative, but it's really accelerated and ramped up its investment in an economic development kind of context in this gap between NQI1 and the reauthorization of NQI. And now you're seeing, Elevate Quantum, Quantum California, Quantum Connecticut, Quantum Capital. Do you think those regional efforts are a necessary ingredient, or is that sort of in place of that more aggressive federal investment, or some other, or is that part of the coordinated effort in your mind?
Yeah, that's a good question. It's a bit of chicken and egg. You're not going to get to the big federal investment until some of the smaller things show something important. So I think it's necessary. I think maybe you're speaking a little bit to the fragmentation that we see, but you know, I think the development tends to happen in these specialized domains, and I think there will be folks, like in Illinois now doing that work. They'll evolve in isolation, but the risk in doing too much of this is it duplicates efforts. It dilutes some of the funding opportunities. Interoperability suffers if everyone's doing everything the way they want to do it and not necessarily to a standard, which is why I sort of promote standards. As much as I hate doing that kind of work, it does pay off in the long run if you can get people to agree. But fragmentation is really expensive when you think about mid-stage translation, going from the lab demonstrations to these scalable platforms. So without alignment across, academia, industry, and national labs and capital markets, you're going to be in trouble. So a stronger coordination needs to happen. Um, I don't want to centralize this stuff either, right? That's the risk that you do in going here. But it's a little bit of both, right? And that's a balancing act that we have to be careful about as an industry. Um,
That's interesting. And I suppose, I mean, one model, the metaphor of the moonshot is brought up in sort of large scale technological advances that need a lot of disparate but coordinated efforts. And the reason is that the space program was this unifying goal that mobilized enormous amounts of capital and human capital and physical and financial capital and physical resources. And we got all kinds of benefits out of it. We got, the
right.
laser and the GPS, et cetera, et cetera, et cetera. Can you imagine, is that potentially a viable model to try to find some big, hairy, audacious goal and try to, at the federal level, try to make that the prerogative, the imperative that helps drive coordination?
I do love moonshots. I do love grand challenges. I think they call to action and they put the spotlight out there, and you drive good talent to work on hard problems. So I definitely think there's an opportunity for things like that to help. That can't be the only way. There have to be some more stable work going on, especially in the discovery area. But when you think about scaling and manufacturability, reproducibility, and the metrology needed at the semiconductor level and all of this, that takes big dollar investments that unless somebody sees profit happening soon, no one's going to make. It's sad. It's good and bad, right? You need profit to drive investment, but
Right. Profit or a national security risk, which, I mean, I think
yes,
you don't call it out specifically. It's not a major focus of the report, but it's sort of implicit that you've even said it in this conversation already, that the spending by other governments, at the very least, is a risk to the United States' position as a leader in this field industrially, but potentially, as we know, I mean, Shor's algorithm was the first thing that captured the popular imagination about quantum computing. There's all kinds of implications to national security that could be brought about by advancing quantum technology. So, do you think that there's an aspect of national security in the future that needs to be part of the motivation for the government's investment in this space?
I most think it's an obvious point to be made here, right? If we break encryption, every old email and text and bank statement that you've ever had in your life becomes open, right? And the enormity of such a risk should be driving someone crazy, right? If not, I'd be very surprised, right? You can say, I got encryption now, we're good. But all that old data people have collected, and then that's available to them. Once they can decrypt that, oh boy, that's a scary moment in time. So I think we need to be really heavily investing from the government to ward off, be there first at the very least, and see what we can do to fend off from anything bad happening if somebody gets a hold of that data. Um, Yeah, I don't wanna
Yeah.
go down that rabbit hole too much, but
Well, and I suppose on the flip side, I mean, quantum communications promises a new standard for unbreakable encryption. Who knows how long that'll last? But
right, right.
that would be a national security risk as well if suddenly, adversaries had unencryptable communications and we did not. That would be a bad position to be in.
Yeah.
Um, Another major theme that I want to touch on before we run out of time, you've got an extensive background in the early days of AI. AI has been, taking the spotlight in many ways, having its, since the Chat GPT moment, as people call it. Um, and there's some interesting things in the report about AI being in your perspective, sort of an aid to the progress, the moving the quantum technologies forward. In what way do you see that happening?
Alright, I'm really glad you asked that question 'cause, um, I I'm going to, talk about this in a kind of a weird way, but the, AI aspect is going to be bidirectional. So, I see, not only AI helping quantum, but quantum helping AI. Um, so I think we need to look at this in a totally different way. So I wanna look at AI in terms of 2 directions, right? There's a converging engineering ecosystems around AI. AI supporting quantum in the has near-term impact, right? Automated calibration, control optimization, noise characterization, adaptive error mitigation, reliability monitoring, fault detection. You got 100,000 million qubits going on. No one person or conventional classical piece of software is going to be able to manage that. You need something that can learn and adapt and immediately and not stop a calculation that's been going on for a month or two. And you're going to need AI to help you do that kind of thing. The materials aspects as well, right? Defect classification, interface analysis, accelerated materials discovery. That's a ripe ground for AI. Process optimization and reproducibility and yield. And then at the systems level, there's this cross-layer, I don't know, modeling algorithm circuit device. You need to look at this design space for exploring new architectures and predictive modeling of performance variability. So AI has got a strong role in helping quantum. Um, and then conversely, in the longer term, I think quantum enhances AI workloads, right? So the potential advantages in the future, you can do optimization problems, sampling, probabilistic modeling, certain linear algebra problems, molecular and material simulations. They'll do those things better. Not everything, but a lot of these things will do better because quantum has been made available to the AI part. So it's a hybrid architecture, right? There's classical AI and quantum accelerators. Quantum is hybrid in itself. It has classical problems as well as, strictly AI solutions that can be done. There's domain specific subroutines and cloud-based integration stuff. Reality check here. Impact will likely be domain specific and not universal. It requires, robust quantum hardware and error mitigation and integration into the existing AI workflows. That's critical. So this intersection of AI and quantum, it's not about replacement. It's about this, we'll call it coordinated evolution across algorithms, hardware, and platforms. So I'm pretty excited and really glad you asked the AI question on top of quantum, because I started off with materials, and I think that underpins all of it. And then you have this AI aspect, which is bidirectional all by itself. So those are really kind of fun areas, I think, and will be fruitful probably in the near future.
Absolutely. Yeah, I agree. And so we've touched on this a couple times, but I want to come back to it as a way to cap off the conversation. You've mentioned standards. You come from an RF background. You were part of the standardization that created the 802.11 standard, which is the underpinnings of everything we do in Wi-Fi, which is pretty important. And clearly, you can see how 802.11 unlocked the value creation in Wi-Fi once there was a standard, vendors could start building hardware, and chipsets could be created for inclusion in handsets and laptops, et cetera, et cetera, et cetera. We have this enormous explosion of innovation and creation of new products and new applications. If you could wave your wand and create a starting place for standardization in quantum today, what do you think the form of that standard would take?
Yeah, that's a good question. I don't have a well thought answer because I have been thinking about this, and start from the bottom and work my way up. I start from the top and work my way down. And things are not mature enough yet for a standard. We don't even know what qubit we're going to be using in the future, right? Um, so I think we should be thinking about the standards and the framework of what a good standard would look like until we see quantum advantage in some reproducible way. I'm not sure we could get to the point of a standard, but I think as soon as you hit that, it's going to be overdue. And
Can't do it ahead of time, can only do it once it's you're too late.
yeah, so this is a real chicken and egg problem.
Yeah.
It doesn't mean you can't start and begin thinking about this, but I don't know of any organization yet that's really taken that on. Been trying to encourage the IEEE to get involved and do this just because I'm familiar with that. You know, the physics community as well probably should be doing something here.
Yeah.
But
Yeah. And there have been IEEE working groups. There's, birds of a feather groups that have come out of IEEE Quantum Week, for example, looking at more the like solution architectures of how do you integrate existing HPC infrastructure or resources with on-premise quantum devices. I think that's an interesting topic. But I agree with you. I think it's those are probably the right conversations to be having, right? It's exploration and thinking through. As you said, I think your formulation is exactly correct. Think through from the bottom up and from the top down, and try to find those contexts where standardization might help that flow for in either direction, the bidirectional kind of interaction you were talking about.
yeah, exactly. Uh, I just want to make sure to underscore, the ERVA report wasn't trying to say, let's go standardize this, but I think as an outcome, that's becoming more and more apparent to me. Um, you know, and just to recap a little bit here, quantum progress, it's no longer about like scientific discovery alone. Because if we miss the opportunity now, we're going to fragment, we're going to dilute and hurt ourselves in the future as we move toward integration and trying to get something that's reproducible and scalable. So I want to really strongly drive us to align, the materials research along with systems design and apply the AI-enabled tools we have and address some of the application needs that are out there now. I think we increase the likelihood that today's breakthroughs become those reliable technologies. I think they can really have lasting impact, but we got a lot of work ahead of us. And I'm just thinking this report opens the door and is that call for everyone to get to work on it. We need that, coordinated engineering ecosystem that'll ultimately drive and determine leadership. But, as we said earlier, it takes investment, right?
Right.
And a whole lot more.
Yeah. Well, Brian, it's been great getting your perspective from the ERVA report, and great to catch up. Thank you so much for your time. This has been really fascinating.
Excellent. It was a pleasure, Sebastian. Always a pleasure.
Thanks again to Brian Gaucher for a great conversation. The ERVA report is really good reading, and I encourage you to check it out. The link is in the show notes. This episode, again, brought to you by qubitsok.com, the signal in the noise for your quantum job search. Learn more at qubitsok.com. If you want to go deeper on the topics we cover, research highlights, commentary, and the occasional behind-the-scenes look at what's coming up for the show, sign up for the newsletter at newquantumera.com. It's free, and it's the best way to stay in the loop. And if you have an idea for a guest, a topic you'd like us to dig into, or just want to say hello, reach out through the website. I read everything. If you're enjoying the show, please subscribe wherever you listen to podcasts and leave a rating or review. It genuinely helps new listeners find us. And if you know someone who's quantum curious, send them an episode. Word of mouth is still how most people discover the podcast. Thanks for listening. I'm Sebastian Hassinger, and this has been The New Quantum Era. Theme music by OCH. See you next time.